All right, let's go through this applications of trigonometry handout. So the first one is sort of a warm-up, just finding all of the sides and angles in this right triangle. Because it's a right triangle and we know two sides, of course we can use the Pythagorean theorem to find the third side. So let's see, the Pythagorean theorem says a squared plus b squared equals c squared. So this is going to give us, let's see, a squared plus b is 4, so b squared is 16, equals 6 squared, that's 36. So moving the 16 over, we get a squared is 20, and so a is the square root of that, so square root of 20. And I think if you simplify that square root, you're going to get 2 root 5. Okay, so 2 root 5. Notice that a is a geometric distance, so it has to be positive, so we don't have to worry about the negative square root here. It's guaranteed to be positive because it's a distance. Okay, so that gives us the side. Now we're going to need to know one of these two angles. Let's call the one in the bottom left theta, and let's call the one in the top right, I don't know, phi, I guess. This is a Greek lowercase phi. We're going to have to use, since we only know one of the angles in this triangle, the right angle, we're going to have to use trig functions to find one of the other two. Let's find theta, I guess. Let's see, and we're going to have to use an inverse trig function because we know about sides and we want to find an angle. I think it would be a little bit easier to use the b and c sides just because they're whole numbers. So that's opposite and hypotenuse for the angle theta. So we need inverse sine. So inverse sine of 4 over 6, or inverse sine of 2/3. So, and let me put myself in degree mode on my calculator. Let's see, so inverse sine of 2/3. I get 41.8 degrees, approximately. Okay, and phi is, well, it's 90 degrees minus whatever theta is. Right, there's 180 degrees in the triangle total. The right angle takes up 90 degrees, so there's 90 degrees left over for theta and phi. So 90 minus theta is going to give us phi. So put that into the calculator. We get 48.2 degrees for phi. Okay, that wasn't too bad. So just with two sides and one angle, we were able to find all of the other measurements in this triangle. Great. Okay, let's look at number 2. All right, we have this 150-foot tall building. It casts a 45-foot shadow, and we want to find the angle of elevation of the sun, which is this angle right here. I guess the sun is supposed to be up here. So we're trying to find how the angle up from horizontal, where the sun is. And let's see, well, it looks like we have a right triangle here formed by sort of the building, the ground, and the shadow. Presumably, this angle that the building makes with the ground is a right angle, I hope, or else it's not a very well-built building. So we have a right triangle. We know two sides. We know the opposite side and the adjacent side to this angle that we want to know. So that unknown angle, let's call it theta. Since we have the opposite and adjacent side, we should be using tangents. So that angle is going to be inverse tangent of the opposite side, 150 feet, over the adjacent side, which is 45 feet. The feet units cancel, which is good because the numbers that go into a trig function, an inverse trig function, should be just numbers. They shouldn't have any units. So now we can dump this into a calculator. So inverse tangent of 150 divided by 45. And my calculator happens to be in degree mode at the moment, which is fine, 73.3 degrees. All right. let's have a look at number 3. So a ship leaves port with a heading of 100 degrees. That's this angle here. A speed of 12 miles per hour. After 1 hour, the ship turns 90 degrees towards the south. So this angle right here is a 90 degree angle. Let's see, this first leg that the ship went down into the right, it's 12 miles per hour for 1 hour. So this side is 12 miles. Okay, and then the ship turns right, 90 degrees towards the south, then slows down to 10 miles per hour for 3 more hours. So that's going to make this 30 miles right here. And an observer measures the bearing to the ship. What angle do they get? So we're supposed to find this big angle here. Okay. Well, this big angle, it looks like it's made up of the 100 degrees we already know, plus this smaller angle that's inside this right triangle that we have. So if we could just find this smaller angle inside the right triangle, then we can add it to the 100 degrees and we will know the bearing. So let's call this angle theta, as usual. And let's see, we know the side opposite and the side adjacent, so we should use inverse tangent again. So that angle theta is inverse tangent of, looks like it's 30 over 12. So let's see, inverse tangent of 30 over 12. So that's 68.2 degrees. And the bearing that we wanted was theta, which is 68.2, plus the 100 degrees. That's this upper arc here. So the bearing that this observer would find is 168.2 degrees. I guess that's a pretty accurate compass if they're measuring tenths of a degree. Okay, now let's have a look at number 4. All right, we have this communications satellite orbiting the Earth at height h miles above the surface. So h is this height above the surface. D is the distance along the surface of the Earth that's within the line of sight of the satellite. So D is the length, is this dotted arc length here along the surface of the Earth. I guess the satellite can't see these points over here because the Earth is sort of shading or blocking the line of sight from the satellite. Okay, and the radius of the Earth is, as usual, 3,960 miles. So I guess that's this distance right here, 3,960 miles. Okay, so part A. Always trouble when there's multiple parts. Find an equation that relates the central angle to the height. Okay, and so there's a hint, just a fact of geometry in case you don't know, that lines coming from the center of a circle and lines tangent to the circle are perpendicular where they meet. So we have this right angle right here. And I don't know, we have this diamond shape. It's actually called a kite shape. But I don't know, we don't really know anything about that kind of shape. But this line that's the height, I noticed that if I extend that down this way, I did a really bad job, but it splits this kite shape in half into 2 right triangles, because we know there's a right angle right there. There's also one here. So, and these triangles are actually the same triangle. They're mirror images of each other. So that means that this angle in the bottom part of our right triangle must be half of the whole angle. Well, the whole angle was called theta, so that means this half is theta over 2. Okay. We're trying to relate theta to the height h. The height isn't a complete side of this right triangle, but it's part of the hypotenuse of this right triangle. So maybe we could use the fact that it's part of the hypotenuse to relate it to the angle. So hypotenuse, also we know this adjacent side because that's a radius of the Earth. So we know the side adjacent to theta over 2. So it seems like since we have adjacent and hypotenuse, we should be using cosine. So let's see, cosine of that angle, and again, that angle is theta over 2, is the adjacent side, which is 3,960 miles. I won't write the units just to save myself a little writing, but this is in miles, divided by the hypotenuse. And the hypotenuse is made up of, there's the height, and then plus, well, there's another radius of the Earth hiding right here. That's also the radius of the Earth, so that's 3,960. Okay. All right, so just writing down the definition of cosine for this right triangle, this left-hand right triangle, gives us this equation. And let's see, well, this equation does relate theta and h, and so this is good enough, I guess. Now let's move on. Part B, find an equation that relates the distance d to the angle theta. So let's see. This diagram up here is a bit of a mess. I've done a lot of work on it. So let me just redraw a simplified version down here. So we have Earth, we have this angle theta, and we have this arc length along the Earth, which is d, and the radius of the Earth was, as ever, 3,960 miles. All right. Well, if we measure this angle in radians, then, d really, it's an arc length. So, maybe a better name for it would have been s. D is an arc length along a circle, and that's the radius times the angle if you're using radians. So have to be using radians to use this equation. But that gives us a relationship between the distance d and the angle theta. D is just the radius, which is 3,960 miles, times the angle theta, if we're using radians. Okay, so I guess that's good enough. All right, so if a satellite needs to cover 3,500 miles, how high should its orbit be? So let's see, this 3,500 miles, that's a value for d, because that's sort of a distance along the surface of the Earth that we need to cover. And we need to find how high its orbit should be. That's h. So we know d, we want to find h. Well, in the previous part, we found a relationship between d and theta. So we know d, we should be able to find theta. But from part A, we had a relationship between theta and h. So we should be able to use theta to find h. So I guess that's going to be our plan. Use d to find theta, and then use theta to find h. Okay, so d is 3,960 times theta. D is 3,500 miles, so that's 3,960 times theta. Then we can just divide everything by 3,960 and we'll have theta. But this will be in radians, so let's see. 3,500 divided by 3,960 equals, so 0.8838 radians. Okay. All right, so now we know theta. Now we need to find h. And let's see, the relationship between theta and h was, it's way up here, cosine theta over 2, so 0.8838 over 2 should be equal to 3,960 over h plus 3,960. So it looks like this time we aren't going to need to use an inverse trig function, just a regular trig function. Be sure you're in radian mode because that angle is in radians. So cosine of 0.8838 divided by 2. Okay, so this left-hand side is 0.9039 equals 3960 over h plus 3960. Now I'm kind of running out of room, so I'm going to try to fit everything in here. Let's see. We can multiply both sides of the equation by this denominator to get this denominator up here, but then also divide both sides by 0.9039. That's going to put that in that denominator over here. So we're going to have h plus 3960 equals 3960 over 0.9039. Okay, and we can do that calculation. So 3960 divided by 0.9039, we get h plus 3960 equals 4,381 and change. And so finally we can subtract 3,960 and we get 421. And this is in miles. So we should plan on getting our satellite up into an orbit that's 421 miles above the surface of the Earth, which is well outside the atmosphere of the Earth. So it should be pretty safe up there.